In the southern sky, approximately 7,500 light-years from Earth, something stirs. Not a planet, not a black hole, not a galaxy, a star. But not just any star. It is a star so extreme, so violently alive, that astronomers struggle to find the right words to describe it. The closest they have come is this: it is a monster, a cosmic monster, waiting at the edge of its own destruction. Its name is Eta Carinae, and for millions of years, it has been building towards something catastrophic. The question is not if it will explode. The question is, when? And what will happen to us when it does? To understand Eta Carinae, you must first understand what it means to be the most luminous star system in our galaxy. Because in a galaxy of 400 billion stars, 400 billion suns burning across 100,000 light-years, Eta Carinae is the brightest, the most powerful, the most dangerous, our own sun, the star that gives us life, that lights our mornings and warms our skin, is, by most cosmic standards, a very average star. It burns at around 5 million degrees Celsius at its core. Its diameter is roughly 1.5 million kilometers. By human standards, it is incomprehensibly large. By the standards of Eta Carinae, it is nothing. Eta Carinae is a binary star system, two enormous stars locked in orbit around each other. The larger of the two contains approximately 90 times the mass of our sun, perhaps more. Some estimates push it closer to 150 solar masses, right at the absolute theoretical limit of how massive a star can physically be before it tears itself apart. Its luminosity, the total energy it pours into space, is 5 million times greater than that of the sun. 5 million times. If you were to place Eta Carinae where our sun sits today, it would not merely light up our sky. It would roast the Earth, sterilize it, in moments. But Eta Carinae is 7,500 light-years away, far enough, in theory, to be safe. Far enough that it appears to us as little more than a faint smudge of light in the southern sky, barely visible to the naked eye, hidden near the heart of the Carina Nebula, or so we thought. Because Eta Carinae has a secret, a history, a past so violent, so explosive, that it has rewritten the rules of what a star is even capable of doing, while still alive. The year was 1843. The world was in the early throes of the Industrial Revolution. Steam engines roared across England. The electric telegraph was being born. And in the southern sky, over the Cape of Good Hope, over the plains of South America, over the jungles of Australia, something impossible was happening. A star that had previously been unremarkable, faintly visible in the constellation Carina, but nothing exceptional, began to glow, and then to blaze, and then to burn with a fury that shook the confidence of every astronomer who witnessed it. By April of 1843, Eta Carinae had become the second brightest star in the entire night sky, surpassed only by Sirius, just next door to us at a mere 8.5 light-years. For a star 7,500 light-years away to achieve this brightness was, by any calculation, extraordinary, impossible even. The astronomer John Herschel, observing from South Africa, watched in stunned disbelief as the star blazed night after night. He had no framework to explain it, no precedent. Stars did not simply do this. What Herschel was witnessing was an event that has no true parallel in recorded human history. We now call it the Great Eruption, and it was not a supernova. The star did not die. It simply screamed. In the span of roughly 2 decades, from the 1830s through the 1850s, Eta Carinae expelled between 10 and 40 times the mass of our entire sun. Let that number settle. 10 to 40 solar masses, ejected, blown off into space, not from an explosion that killed the star, but from a paroxysm, a stellar tantrum of almost incomprehensible violence. The energy released during the Great Eruption was equivalent to nearly all the light our sun will emit over its entire 10 billion-year lifetime, released in a few decades. The gas and dust ejected during this event formed what we now call the Homunculus Nebula, a twin-lobed cloud of material surrounding the star like a cosmic cocoon. It is visible today through telescopes, still expanding outward at speeds of roughly 650 kilometers per second. The Homunculus Nebula has become one of the most studied objects in astronomy, not merely because of its visual beauty, but because of what it tells us. It is a record, a fossil of violence. Frozen in gas and light, the history of one of the universe's most extraordinary stellar events. But the Great Eruption of 1843 was not the first time Eta Carinae had convulsed. Studies of light echoes, Light from the original eruption that bounced off distant gas clouds and only reached us centuries later revealed a second, smaller eruption had occurred sometime around 1250 CE. Perhaps earlier, there were more. Eta Carinae is not just dangerous, it is repeatedly, habitually dangerous. The reason for this instability lies deep inside the star's core, where physics is pushed to its absolute limit. Stars the size of Eta Carinae live precariously balanced lives. On one side, gravity. Immense, crushing, pulling inward with trillions of tons of pressure. On the other side, radiation. The outward pressure of the energy generated by nuclear fusion at the core. In most stars, these two forces balance. The star finds an equilibrium and maintains it for millions or billions of years. Our sun has been in this balance for approximately 4.5 billion years and will remain so for another 5 billion. Eta Carinae does not have this luxury because it is so massive, so grotesquely, outrageously massive. The radiation pressure inside it approaches something called the Eddington limit, a theoretical boundary beyond which the radiation pressure becomes so intense that it begins to overwhelm gravity itself. When a star flirts with its own Eddington limit, catastrophic things can happen. Material can be driven off the surface in violent eruptions, not supernovae, but what astronomers call luminous blue variable episodes. The star essentially blows off part of itself, not as a death, but as a pressure release. Like a steam boiler with a broken valve. Eta Carinae is the most extreme example of a luminous blue variable ever observed. It has become the defining object of this entire class of stellar phenomena. A case study in what happens when a star becomes too large, too luminous, too powerful for its own good. But here is what keeps astronomers up at night. Because Eta Carinae is not merely unstable, it is dying. Perhaps not today. Perhaps not in our lifetimes. But in cosmic terms, Eta Carinae is living on borrowed time. And when it finally goes, when the balance finally tips and the core can no longer sustain itself, it will not go quietly. When Eta Carinae finally reaches the end of its life, astronomers believe one of two things will happen. Either it will collapse into a neutron star, releasing a supernova explosion of extraordinary power, or, and this is where things become truly terrifying, it will collapse so rapidly, so completely, that it skips the neutron star phase entirely and plunges directly into a black hole. And in doing so, it will produce not just a supernova, but a hypernova. A hypernova is one of the most violent events possible in the universe. A standard supernova, already a catastrophe of unimaginable proportions, releases approximately 10 to the 44th joules of energy, a number so large it is essentially beyond human comprehension. A hypernova can release 10 to 100 times more, in a matter of seconds. But it is not merely the total energy that makes hypernovae so dangerous, it is the way that energy is delivered. Because in the most extreme cases, when the rotation of the collapsing star is fast enough, when the magnetic fields are strong enough, a hypernova produces something else entirely. A gamma-ray burst. Gamma-ray bursts are the most energetic explosions in the universe. In a fraction of a second, a long gamma-ray burst can release more energy than our sun will emit over its entire 10 billion year lifetime. This energy is not dispersed in all directions like a standard supernova. It is focused, collimated, beamed outward from the poles of the dying star in two incredibly narrow, incredibly powerful jets. The beam itself may be only a few degrees wide. But if you are in its path, if you happen to be in the direct line of those jets, the consequences are extinction level. Here's the question that matters most. Here's the question that has been quietly haunting astronomers for decades, since we first understood what Eta Carinae was truly capable of. Is Earth in the path of the beam? The answer is complex, and the complexity is not comforting. We know that Eta Carinae's rotation axis, and therefore the likely direction of any gamma-ray burst jets, is tilted roughly 40 to 45 degrees relative to Earth. This is significant. At that angle, the narrow cone of a gamma-ray burst would almost certainly miss us. Almost. The word is doing enormous work in that sentence. Because gamma-ray burst jets are not perfectly precise instruments. They are not laser beams fired with surgical accuracy. They are chaotic, turbulent, unpredictable rivers of high-energy plasma, shaped by magnetic fields and rotation rates we can only estimate. The uncertainty in our models of where the jets would actually point is large enough that we cannot rule out Earth being clipped by the edge of a beam. Not hit directly, but struck by the outer edge of an expanding gamma-ray halo. If even a small fraction of the gamma radiation from an Eta Carinae hypernova were to reach Earth, the effects would be profound. Scientists have modeled this scenario extensively. The gamma rays would interact with our atmosphere in a cascading chemical reaction, producing massive quantities of nitrogen dioxide, the same compound that gives smog its brown color. This nitrogen dioxide would temporarily turn our sky brown, blocking sunlight and dramatically reducing temperatures for months or years. But far more critically, the same radiation would destroy ozone. Not a percentage of the ozone layer. A significant fraction of it, potentially 30 to 50% of the total global ozone shield, according to some estimates. And this destruction would not be temporary. Ozone layers take years, even decades, to fully recover. An ozone layer reduced by half means ultraviolet radiation from our own sun. Radiation that our bodies evolved to withstand in modest doses would reach the surface in amounts that would devastate ecosystems. The base of the food chain, phytoplankton in the oceans, the microscopic organisms that produce roughly half of Earth's oxygen and support all marine life, would be decimated. Without phytoplankton, the oceans collapse. Without the oceans, the land follows. Some scientists have proposed that a gamma-ray burst striking Earth in the past may already have caused one of the 5 great mass extinctions in our planet's history. The Ordovician extinction, approximately 450 million years ago, wiped out around 85% of all species on Earth. Its cause has never been definitively established. Some researchers believe a gamma ray burst from a dying star, now long since gone, its light having faded into the cosmic background, may have been responsible. But here's what makes the story of Eta Carinae more than a horror story, more than a tale of cosmic danger and existential threat. Because Eta Carinae is also one of the most scientifically valuable objects in the known universe. A living laboratory for stellar physics, operating at extremes we cannot replicate on Earth or model purely in computers. For decades, the Hubble Space Telescope has trained its eyes on Eta Carinae, watching, measuring, cataloging. And what it has found has transformed our understanding of how the most massive stars live and die, the binary nature of the system. 2 massive stars orbiting each other in an eccentric elliptical orbit that takes about 5.5 years to complete, creates conditions unlike anything else we can study. When the 2 stars approach each other at their closest point, their stellar winds collide with the force of warring hurricanes. The collision zone glows brightly in X-rays, allowing astronomers to precisely track the orbital period and study how stellar wind interactions shape the environment around massive stars. The 5.5-year cycle is so regular, so reliable, that astronomers around the world schedule their observations around it. Eta Carinae has become, in a strange way, a kind of cosmic clock, a rhythmic pulse in the southern sky that researchers use to test and refine our models of stellar evolution. And it is brightening. Year by year, decade by decade, Eta Carinae is becoming more luminous. When it dipped to bare naked eye visibility in the early 20th century, astronomers assumed it would fade entirely. Instead, it has been gradually increasing in brightness for the past century. Something is changing inside the system. The internal dynamics are shifting. The star is evolving, and not toward stability. Eta Carinae is not alone in the Carina Nebula. This region of sky, spanning roughly 300 light-years across, is one of the most productive stellar nurseries in the entire Milky Way. It contains multiple massive star systems, stellar clusters, and regions of active star formation. It is, in many ways, the cosmic equivalent of a violent, overcrowded city, brilliant, chaotic, and dangerous. The most famous other resident is the Trumpler 16 cluster, a dense grouping of hot, massive stars, several of which are themselves enormous enough to eventually produce supernovae. Eta Carinae, however, still retains a significant fraction of its original hydrogen envelope, which is part of why the Great Eruption of 1843 was not a supernova. It still has fuel left to burn, still has outer layers to blow off before the core is exposed. But with each eruption, each spasm of stellar violence, it sheds more of that envelope. It is inch by inch, year by year, stripping itself down to its core. When the last of that envelope is gone, the countdown to explosion will accelerate dramatically. The question everyone wants answered is simple: when? The answer, as is so often the case in science, is deeply unsatisfying. We do not know. We cannot know, not with the precision that the question deserves. What we can say is this: by any cosmic measure, Eta Carinae is close to the end of its life. Stars of this mass typically live for only 2 to 3 million years. Eta Carinae is estimated to be roughly 3 million years old. It may already be past its expected lifespan, sustained only by its own extraordinary, aberrant nature. The explosion could happen in 10,000 years. It could happen in 100,000 years, by the standards of human civilization, by the standards of recorded history, which covers barely 5,000 years. Those timescales are incomprehensibly distant. We will not see it. Our children will not see it, but it could also happen in 100 years, or 10. Or, though astronomers consider this unlikely, it could be happening right now, 7,500 light years away. With the light of that explosion racing toward us, even as these words reach your ears, racing toward us at the speed of light, and we would not know, cannot know, until the light arrives. This is one of the most disquieting aspects of observational astronomy. The stars we see are not the stars that exist. They are the stars that existed. When we look at Eta Carinae, we see it as it was 7,500 years ago. In the time of ancient Egypt, when the first pharaohs were building the earliest temples, the light now reaching our telescopes was just beginning its journey. What has happened since? We do not know. We are watching a broadcast from the deep past, with no way to see the present. If Eta Carinae exploded today, the real today, not the today we see in the sky, the light from that explosion would take 7,500 years to reach us. Our descendants, perhaps 100 generations from now, would wake one morning to find a second sun blazing in the southern sky. For weeks, perhaps months, it would be visible in broad daylight. At night, it would cast shadows. It would be the most spectacular astronomical event in recorded human history. And depending on the nature of the explosion, whether it produces a focused gamma ray burst, whether that burst happens to point toward Earth, it could also be the most dangerous. The good news, if good news can be extracted from this story, is that astronomers will not be caught entirely off guard. In the final stages of a massive star's life, changes begin to appear that can be detected with careful observation. The star may brighten significantly, as Eta Carinae has been doing. Its spectral signature will shift as surface temperatures change and new elements are exposed. And critically, in the final moments before a core collapse supernova, the dying star releases a massive burst of neutrinos, ghostly, near-massless particles that pass through ordinary matter as if it does not exist. These neutrinos travel at nearly the speed of light, arriving at Earth just hours before the light of the explosion itself. They would be detected by neutrino observatories around the world, giving humanity a warning that something is about to happen at Eta Carinae. Facilities like the Ice Cube Neutrino Observatory at the South Pole, a cubic kilometer of Antarctic ice studded with thousands of sensitive light detectors, are specifically designed to catch these signals. When supernova 1987A exploded in the Large Magellanic Cloud, neutrino detectors around the world registered a pulse of particles hours before the visible explosion was observed. For Eta Carinae, which is roughly 30 times closer, the neutrino signal would be proportionally stronger, unmistakable. The detectors would light up, alarms would sound, and humanity would know, with hours to spare, that something extraordinary was about to happen in the southern sky. Whether those hours would be sufficient for any meaningful preparation is another question entirely. And so we arrive at the final question, the most human of questions. What do we do with this knowledge? Because we are, as a species, unique in our corner of the universe, in our ability to know that such threats exist. The phytoplankton in the ocean do not worry about gamma ray bursts. The forests do not know that above them, in the southern sky, a star is slowly building toward an explosion. Only we know. Only we can look at the universe and understand, however imperfectly, what it is capable of. This knowledge is both a burden and a gift. It is a burden because the dangers are real, even if distant and probabilistic. It is a gift because knowledge, unlike ignorance, can be acted upon. We cannot deflect a gamma ray burst. We cannot build a shield against radiation traveling at the speed of light. If the jets from a hypernova were aimed directly at Earth, there would be no engineering solution. The physics are simply too extreme. But preparedness can take other forms: monitoring, early warning systems, an international network of neutrino detectors and gamma ray observatories capable of providing the hours of warning that the physics allows. Models of atmospheric impact that can guide decisions about food storage, agricultural resilience, and ozone monitoring. And perhaps most importantly, the humility that comes from looking at Eta Carinae and understanding our place in the universe. We are a species on a small world orbiting an unremarkable star in one arm of a middle-sized galaxy. And 7,500 light years away, a monster star is burning through its last reserves of fuel. The universe is not built for our comfort. It is not arranged around our survival. It simply is, vast, violent, and indifferent. And yet, despite this indifference, despite this scale, despite the fires burning 7,000 light years away, here we are, a species of tool users, storytellers, scientists, and dreamers. A species that looked up at the sky and instead of simply fearing what it saw, began to ask questions, began to measure, began to understand. We did not have to understand Eta Carinae. We could have lived our lives beneath it, never knowing what it was or what it was capable of. But we chose to look. We pointed our telescopes at it. We analyzed its light. We built mathematical models of its interior. We read the record written in the Homunculus Nebula and understood the story it was telling. This is what makes us remarkable. Not our safety, not our permanence dot, but our insistence on knowing. Tonight, Eta Carinae burns, as it has for 3 million years, as it will continue to burn for now. Its light is traveling toward you across 7,500 light years of space, crossing vast clouds of interstellar gas, passing dead stars and newborn nebulae, threading through the spiral arm of the galaxy and out across the emptiness between the stars. And when it reaches your eyes, when that ancient light completes its journey, it carries a message. Not a warning, not a threat. Something older than either of those. A reminder. The universe is alive. It is not a backdrop, not a painting hung behind the business of human civilization. It is a living, evolving, violently dynamic place, filled with objects of terrifying power and incomprehensible scale. And we are part of it. Small parts, temporary parts, but knowing parts. Eta Carinae will die. Perhaps not in our lifetime. Perhaps not in 1,000 lifetimes. But it will die, as all stars die. In fire and collapse and the release of energies our minds were not built to hold. And when it does, somewhere, in a future we cannot see, someone may be watching, looking up at a sky that blazes with the light of a dead star. And perhaps they will ask the same question we are asking now. Not just, what was that? But what does it mean to live beneath such skies? In a universe so vast, so violent, so indifferent, and yet, somehow, so impossibly, breathtakingly beautiful.